Okie doke. So let's just kick straight off. If my computer will let me. There we go. So let's have a look at gamma ray bursts. And so the first question is, well, what the heck are they? Well, they're either the consequence of two supermassive stars, most likely Wolf-Rayet stars collapsing to form a black hole, or two neutron stars combining, and this has been now confirmed. This was a theory up until relatively recently by the Virgo and LIGO things, where the gravitational waves were coincident with gamma rays from the same part of the sky. So they are that, but the thing is, in a few seconds, they release more energy than the sun will in its 10,000 million years of lifetime. And what you get, which you can actually see in the drawing, artist's impression, first one, you get flares of gamma ray energy emitted in opposite directions. And these have been quite sort of enigmatic ever since they were discovered. Part of the problem with these is, or the discovery of these, it was military equipment. Just after the Second World War, people were looking to try to make sure, monitor nuclear explosions and all the rest of it. And so a lot of the early stuff was secretive, but now it's much more available. And when they were first suggested as being around, as being a thing, someone suggested, well, maybe this might account for the Fermi paradox. So what is the Fermi paradox? When the search for extraterrestrial intelligence started, Frank Drake had worked out how many communicating civilizations there might be in a galaxy the size of Milky Way, came up with something like about 50,000. And why haven't we discovered any? And one of the suggestions was that, well, maybe they've been wiped out by gamma ray bursters. So there are actually much better solutions to that question. One of which is basically it's a probability thing. So if one hits us, well, we get one in our galaxy, and it's pointing this way, destroy the ozone layer, bombard one side of the Earth, because they're very quick, these things. So it wouldn't bombard both sides of the Earth. Lethal radiation, the consequence would be mass extinction, food chain disruption, and starvation. What a nice way to go. But it's only a problem for planets in the beam. And now we've got two things. One is that we are a pretty small target. And the other is that the beam has a mean angle of about 5 degrees. So it's actually going to miss more than it's going to hit. So we're lucky in that way. But with any calculation of risk, you need to know what the frequency of these things are. There's up to 1 million a year of the long gamma ray bursters, those are ones that last over 2 seconds in a galaxy the size of the Milky Way, and we detect at least one per day from the universe. And the short ones, less than 2 seconds, nobody has a clue. So part of the problem is, as we all know, a lot of stuff with astronomy just doesn't work on human timescales. And most stuff with stellar evolution is much longer than a human timescale. So we're talking about millions, billions of years. Gamma ray bursts are much shorter. And part of the thing we're doing now is you've got things like the Fermi telescope, gamma ray telescope. And what that does is if it detects a gamma ray burst, it immediately messages ground-based telescopes with essentially stop what you're doing unless it's incredibly important and look there, so we can try and find out more about these things, because we actually know remarkably little about them. It has been suggested that maybe the Ordovician-Silurian extinction, one of the great extinctions, the one that got rid of the trilobites, might have been caused by a gamma ray burst. There's lots of other suggestions for that as well, so we don't really know. It's very difficult when you're going back, sort of nearly 500 million years to get a real handle on what's going on. But that has been one of the suggestions. So with anything like this, if we've got some sort of hazard around, well, do a risk assessment, don't we? So what can we do about them? And you're going to start seeing a theme coming up in this talk. And the answer is absolutely nothing, because we won't know about them until they hit, because gamma rays travel at the speed of light. Information can't travel faster than the speed of light. Sorry, it's hello. If you've got a question, can you put it in chat, please? So nothing, everything travels at the speed of light, and well, so we have no way of knowing. Right. So what is the risk? Well, it's so small nobody's ever bothered to calculate it, but it's considered to be infinitesimally tiny due to narrow beam angle and ultimately us being not a huge target either. But then we come on to things like magnetars. Now, they've been in the news more recently. They've been suggested as a source of fast radio bursts, which they're almost essentially are. So what are they? They are neutron stars, but they're not like the pulsars, which rotate tens or hundreds of times per second. These are slow rotating things. They are round about 1 rotation per second to 1 rotation per 10 seconds. So they're really tiny. They're about the size of a town, and they've got more mass than the sun. And they emit gamma rays in all directions. So you have effectively an omnidirectional gamma ray burster plus a huge electromagnetic pulse. And so, to liken this word, it's sort of like, to bring a cruise missile to a boxing match or something like that. It's just not fair. And there's thought to be about 30 million of these things in the Milky Way. So if one of them went off near us, and they have gone off quite near us occasionally, gamma is not lethal, could lead to long-term radiation sickness, and could knock out communication satellites. This is the electromagnetic pulse. If that happened, we would have global economic collapse. If you've ever been in a country which is doing that, I'm a Rhodesian Zimbabwean by upbringing, and I was in Zimbabwe when it underwent its economic collapse. It's not a pretty sight, and that on a global level could be horrible. It would lead to chaos. We think we're in economic chaos now. Nothing compared to what would happen if we had our communication satellites knocked out by a gamma ray burster. So how frequent are they? Well, first one was discovered in 1979, and we've been hit at least twice more. The Neo-Schumacher probe, which was sent to asteroid Eros, I think it was had to be shut down to avoid damage, and that was a gamma ray burst about 20,000 light years away. And then about 16 years ago, one affected the ionosphere, and that was from about 50,000 light years away. And the nearest one is a mere 9,000 light years away. Now, if we just do a quick look at inverse square effect, that would have more than 4 times the effect of the one that hit us from 20,000 light years away. So, we do have reason to be cautious about these things. So what can we do about them? As I said, there's a theme. Nothing we won't know about until they hit. What's the risk? Well, there's actually a pretty high risk of satellite disruption. And this is why we do need to be building more resilience into our satellites. But the risk of, sort of Armageddon wiping us all out because of this, because the gamma ray radiation is omnidirectional, not beamed, it's actually nowhere near as intense as you get from a gamma ray burster. So the Armageddon risk is pretty small. So let's move on to something we can do even less about in a way. And that's cosmic rays. You've probably seen this image before since Tim Peake came back from the ISS. This did the rounds quite a lot. It's actually been around long before he went up there. So what this image is showing is artist's impression of gamma rays coming and interacting with particles in the atmosphere, splitting them and causing cascade effects. So what you get is you get a huge oval on the ground or on the sea, on the surface of the Earth, and something like the Cherenkov telescope array, which has been set up, by looking at the shape of the oval, you can actually tell where the things come from and stuff like that. Okay, so what are they? Well, they're very high energy particles, and they originate in hypernovae, or kilonovae, some people call them nowadays as well, which are the supernova of incredibly massive stars. And they can have energies millions, tens of millions times greater than we get in something like the Large Hadron Collider. The one with the greatest energy ever found, you've probably heard of the God particle. They call this one the Oh My God particle. It was almost certainly an iron nucleus, and the energy that this single atomic nucleus had was said to be equivalent to the energy of a tennis ball hit by Andy Murray as hard as he could in his prime. So we're looking at something, you know, and this is a single atomic nucleus with that amount of energy. That's why they call it that. It's absolutely phenomenal. And they have discovered others like that as well. But that particle like that, even if it hit you, just goes straight through you. So that's really not a huge problem. Wouldn't interact that much with you. The problem is that they cause secondary radiation where they enter the atmosphere, and that secondary radiation, although it's lower energy, is the stuff that can harm us. So we get gamma, beta, and alpha radiation coming off from that. And what it can do is it can muck about with our genetic code, so cause double-stranded DNA deletions. Okay, we get genomic instability. It's not necessarily a bad thing, because if genomic instability wasn't a thing, then we wouldn't be here. We would still be, you know, sort of like bacteria in the primeval swamp. So we've actually, it's quite useful that there is such a thing as genomic instability. I'll say, you know, everything on the planet is genetically modified, just not by humans, by natural processes. But the other thing it does is it mucks about with computer chips. And you get a flip bit, a 1 goes to a 0, or a 0 goes to a 1. And the average is 1 error per 256 megabytes, you can see there, of RAM per month, which is not too horrendous if you're down at the surface of the Earth, sea level. If you're somewhere like the space station, it's a lot worse. It's not just Microsoft Windows. Actually, I don't even know if these Microsoft Windows. It's just not Microsoft Windows being unstable, so they have to reboot their computers so often. It's just good common sense. They are sometimes implicated with mucking about with avionics. There was a case of a Qantas airliner going from somewhere from Australia to somewhere else, and the avionics suddenly told the pilot, you are going up at an angle of 60 degrees. So he immediately corrected that manually. And of course, what he did is put himself into a dive of 60 degrees in order to correct that. And our passengers found themselves sort of adhered to the ceiling. You know, and a few were actually hospitalized from that. So this is a real risk. I mean, one of the things I'm not talking about in this talk, because it's a whole talk in itself, is space weather. And space weather is another one that can muck about with avionics as well. So how frequent are these things? Well, they're constant. You can't get away from them. They even penetrate the surface of the Earth, so you get them underground. So let's say the theme continues. What can we do about them? And the theme changes. Live at low altitude. That's the best thing you can do if you want to avoid gamma ray risk. You live at low altitude, because the higher you are, the more at risk you are. So things like aircrew and astronauts receive a much higher dose than the rest of us. Now, don't worry too much about what a sievert, or in this case a millisievert, is. It's a measure of radiation which accounts for the intensity of the radiation and its ionizing potential. So something like an alpha particle, for example, is much more likely to ionize something than a gamma ray or something like that if they have the same energy. So aircrew astronauts' safe limit is thought to be about 1 millisievert per year, which is what we get if we'd had there, as we see there, 7 16-hour flights at 30,000 feet, cruising height of a jumbo jet. Aircrew typically receive 3 times as much. And this is why people who do those sort of things, they are statistically at a higher risk from certain cancers and such like that. So cosmic rays, a real thing. They're there, and the universe is gradually actually modifying us with that. Actually, viruses do a lot of genomic modification in mammals as well, and birds. Right, moving on. Hypervelocity stars. Well, what they are is stars that hurtle at an enormous pace through space. Excuse me. So how do they form? If you know your globular cluster theory, when they started looking into the depths of globular clusters, Hubble Space Telescope actually did quite a lot of this, they noticed there were quite a few blue stars there. Now, the whole theory of globular clusters at the time was that they formed as clusters of stars when the galaxy formed, when the Milky Way formed, and formed a halo around because of that. I mean, it's changed slightly since then, but not much. If they're that old, we should have red stars or reddish stars, not hot blue stars, which are essentially young stars. So what on earth is going on? And initially they called them blue stragglers. The idea being that they are straggling behind in their evolution. But what is essentially happening is something that is part of the process that we get with hypervelocity stars. So if we look around here, what we get in a triple star system, a black hole at the center of the Milky Way. We have a triple star system moving there, or the center of any other galaxy. And what happens, one star falls in, and then a binary pair recoils. As the binary system leaves the galaxy, they merge, and they form a blue straggler. And the blue straggler then hurtles through intergalactic space. So if one came here, we'd get something, it's a star traveling at around about 1 million miles an hour, which is pretty quick. And we'd get intense gravitational disruption. It wouldn't have to be a direct hit or anything like that. Again, you know, we're down to the tiny target thing. But it would only have to pass within a light year or two of us. And it would cause disruption to the Oort cloud, and which could then start triggering stuff like comets and cometary debris coming in. If it came even closer, it could disrupt the orbits of planets, and that would cause cataclysmic collisions within the solar system. We know about 34 of these things, and another 5 at the latest count possibles of these. Fortunately, none of them is headed this way. The nearest is 70 light years away, and we would get at the speed they travel about 675 years warning per light year. So we've got a long, long time to consider what we're going to do about these things. Longer than any meaningful civilization has lasted on Earth, has yet lasted on Earth. So what can we do about them? Well, nothing. But we can detect them a long time before they hit. It would be actually even longer if all they were doing was Oort cloud disruption, so we get another heavy bombardment. It's going to take tens of thousands of years anyway for cometary debris to get here from the Oort cloud to us if it's disrupted. So it's a long time. But at least those people with the end is nigh signs, for once they'll be right, just not in their lifetime. So what's the risk? Well, again, it's this tiny target. Although the target, you know, let's try and get an idea of target size on this sort of thing. If we take the sun as being the size of, say, a basketball, The Earth is about a 2 mm pinhead, just over 20 meters away. On that scale, the entire solar system out to Neptune is a mere half mile. So just the Earth or the Sun or anything in the scale of that, there's a lot of space for stuff to fall through. If we take that even further on that scale, the distance to the nearest star is going to be about 2,500 miles. We'll use another scale a little bit later on. So there's a lot of intergalactic space. There's a lot of interstellar space, a lot of space in the solar system. We see this as well with things like computer games or sci-fi movies where people are orientating, curving their way through asteroid fields. Well, no, the mean separation of asteroids in the densest parts of the asteroid belt is about 1 per million kilometers. They're not very, very closely spaced. It's, as an analogy, it would be like trying to navigate a grain of dust through a field of baked potatoes when the potatoes are a mile apart on average. So no, it's not a huge chance that something's going to get hit at all. Although because of the disruption thing, we are no longer that little target, we are a big target. We're probably on that scale, something effectively a target about a mile in radius on that scale. But we are still a tiny target in the greater view of things. Well, at least hypervelocity stars we can see. Black holes, of course, we can't see. At least we can't see them directly. They're probably gravitational wave kick from black hole merger. So what you get is black holes traveling through space, again, at several million kilometers an hour. The problem is the only way you can detect them is by their effect on the light of the things behind them. Because they will, by the time, if by the time they've merged, they will have consumed all of the gas surrounding them after they've been thrown out of their home galaxy, assuming they formed in a home galaxy. There's actually no necessary reason that a black hole needs to form in a galaxy. So how they get us? Again, it's this massive gravitational disruption. But again, it's only related to its mass. So just because it's a black hole, it doesn't have any more gravitational disruption than a star of the same mass at the same distance, unless, of course, it gets close because it's smaller, so it can get closer. If that happened and it came really close to Earth, well, Earth could be ripped apart, spaghettified. If you don't know about spaghettification, this is where the gravitational gradient is so great. Imagine that you are going in feet first. The gravitational pull on your feet, it's so much greater than the gravitational pull on your head that your feet accelerate in faster than your head and you sort of get stretched out and spaghettified. If it only came close, we're back to this Oort cloud disruption and sending down debris on us again, tens of thousands of years later, of course, like something like the late heavy bombardment, which was not a bad thing because when that had happened, the Earth had differentiated. So all the interesting stuff most of the interesting stuff had sunk into the core, and the late heavy bombardment delivered the stuff that we build our world out of, a lot of the heavy metals and stuff like that. So gold and such like, delivered about 3.9 billion years ago by asteroids and comets and whatever the late heavy bombardment was. So at least we've got that stuff in the Earth's crust and we can be here, so it's a good thing. How frequent are they? Well, they're blooming difficult to detect, and the answer is nobody knows. Nobody really has a clue. What can we do about them? The theme returns, absolutely nothing. And what about the risk? Well, someone has actually calculated this, believe it or not, and there are 16 zeros there. So that is a risk of 1 in, I haven't a clue how to say that number. I just thought it looked more impressive with the 16 zeros than just writing 10 to the power of 16, which we can do. Yeah. It's a huge number, so certainly not worth wasting sleep about. Okay, we're losing sleep over. Let's move on. Rogue planets. As you can imagine, something that doesn't have its own light and is relatively tiny, star to planet, think, sort of basketball to pinhead, is going to be pretty blooming difficult to detect, and yet they are detected. So they're planet-sized bodies, might be ejected from its star system, might never have gravitationally bound to any star. There's no actual reason the planet has to have been bound to a star, as far as we know, and they just orbit the galaxy directly. Again, collision with the Earth, extremely low probability, tiny target, blah, 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 or disruption of the Oort cloud. Have to be quite close, but that is certainly a possibility. So how many are there? Well, we don't know. The low estimate is somewhere between 1 for every star in the Milky Way and 1 for every 2 stars in the Milky Way. It might, now people think it might be a little bit high. It might even be 2 per 1 star in the Milky Way. But yes, that's quite a lot. The high estimate is 100,000 per star in the Milky Way. And the huge error bar, because these things are so difficult to detect. And we have detected several of them. The nearest one is this one. I won't bother to read out its name. You can read that for yourself. It's 130 light years away. The discovery of that was announced in September 2012. And some of you might remember what was going to happen in December 2012. The Mayan apocalypse, where somebody said, yes, Planet X is going to come and hit us, and all the rest of it. Well, of course it didn't. We're still here. But it spawned lots of books and lots of movies and lots of arguments on the internet and all the rest of it. But when this was announced 3 months before the Mayan apocalypse was about to happen, a lot of the conspiracy theories, you see, because this one is coming our way actually, came up with, yeah, you see, we were right. This is it. This is the one that's going to get us. Well, hang on, folks. It's 130 light years away. How fast does it have to be traveling to get here in 3 months? We say, never allow a complete ignorance of physics to get in the way of a really rubbish conspiracy theory. But what can we do about them? And of course, the theme is there still. It's nothing. Risk, well, I think as I've put here, just not worth losing sleep over. Let's change tack, because this is all stuff coming from outside. What about stuff that happens from inside? Because our Earth is still part of the universe. Now, I don't know if you've come across Verneshots before. If you've ever read Jules Verne's book about getting people to the moon, you might recall how he did it in that. And what he did, it was basically a huge cannon. And this is essentially what the notion of a Verneshot is. Now, they're hypothetical. Some geologists, I have to admit, not so many nowadays, but certainly a couple of decades ago, this was thought to be a high probability of something that could happen. And the idea is you get this build-up, a huge build-up of carbon dioxide underneath the craton. A craton is a bit of really, really old, thick crust. Now, this would be nothing like the postulated supervolcano under Yellowstone National Park or anything like that. This makes things like that pale into insignificant. And the idea was that it might be forceful enough, get enough of a build-up to launch a huge amount of crust and mantle into a suborbital trajectory. So a massive bang. And this was one of the things that was postulated as being responsible for, possibly for one of the mass extinctions. But then you have something else happening. What you're left if that happens, you're left with this enormous void in Earth's crust and a bit of magma below it. So that whole thing collapses at quite a rate. So you get a hypersonic shockwave, which hits the remains of the craton, the remains of your thick continental crust, and pulverizes it with an explosion of, calculate, about 120 gigatons of TNT. So we're talking about something about 60 million times the power of the Hiroshima bomb. Well, that's fine. But then you get about 20 gigatons of debris blasted into the atmosphere, and lava fills all the holes that's left behind. That's great. But remember, we've had that bit of crust that's been knocked into a suborbital trajectory, and then that lands somewhere else because Earth has rotated underneath it. Isn't that good? And it's exactly like an incoming asteroid, which we'll look at later, but much, much less warning. And of course, though, also much lower velocity. And because the energy of an impactor is related to the square of its velocity, then we get much, much less damage than from a similar size asteroid. Well, how frequent are they? Well, they may never have happened. It was, when they were postulated, suggested that one of them might have been responsible for the Tunguska event, been postulated that what happened in the Deccan traps and Siberian traps might have been a similar sort of event. We don't know, almost certainly not nowadays, though. So we don't really think this anymore. But these are things that have been postulated. And again, what can we do about them? Well, you know the answer to this already. You know, we just have a big course about nothing. What's the risk? If I was actually visiting you now, this would I'd be looking for the nearest exit, because actually possibly zero, because they probably don't exist. So I've just wasted the last 3 or 4 minutes of your life. So let's move on to something that does exist. Galactic collisions. So what are they? Again, well, exactly what it says. 2 or more galaxies collide and interact, and there's a strong star formation as interstellar gases combine. And this is the Antenna Nebula. Actually, I didn't put this in because this had been in for a while. I think it's the astronomy picture of the day, the Antenna Nebula. I seem to remember seeing as I was on my interweb this morning. So you get lots and lots of star formation. So how will they get us? Well, we need to start looking again at this scale of star sizes and the spaces between them. Let's scale it down a little more. So if we take a sun-sized star as being approximately the same size as a ping pong ball, the average separation in the spiral arms of the galaxy is ping pong balls about every 500 miles. And even where they're really, really densely packed in the core of the galaxy, you're talking about ping pong balls every few miles. So there's an enormous amount of space. When this happens to galaxies, what happens effectively is you don't get stars annihilating each other. You get, well, I'll show you a little bit later what you get. So unless there is this direct interaction between another star in our solar system, we could escape completely unscathed. Okay. If there is direct interaction with the solar system, it's most likely again to be this massive gravitational disruption that has come about with just about everything else we've looked at so far, apart from the electromagnetic versions. So hypervelocity stars, rogue planets, rogue black holes. So that's the thing there. So that's an ever-present danger. But say, you know, if it happened, we've still got another 10,000 years or so at least. How frequent are they? Well, they're happening around us all the time. That's why we've got all these pretty pictures of them. What can we do about them? Well, nothing. We know that. There's absolutely nothing we can do about them. Risk? The risk is certainty. It is going to happen. Probability 1. So in about, depending on whose sums you look at, about 4.5 million years' time, M31 and us, M31, the Andromeda Galaxy, will eventually merge and eventually form an elliptical galaxy. And looking at that, people have actually tried to map how it would happen. And here is a little video showing you what's going to happen there. They keep the caption on for a long time, so you've got lots of time to read it. Timescale bottom right. And there we are, left with our elliptical galaxy, and Triangulum galaxy still there, alive and kicking, as it were. So that's 8 in approximately half the time we got. We threw 8 of the 10. So what's happened? What's gone wrong there? Well, absolutely nothing. I'd like to read you something before we carry on. This is from a book called Rendezvous with Rama, which some of you may have read, Arthur C. Clarke. Sooner or later, it was bound to happen. On June 30th, 1908, Moscow escaped destruction by 3 hours and 4,000 kilometers, a margin visibly small by the standards of the universe. On February the 12th, 1947, another Russian city had a still narrower escape. That was Vladivostok, the Sikhote-Alin impact, when the second great meteorite of the 20th century detonated less than 400 kilometers from Vladivostok, with an explosion rivaling that of the newly invented uranium bomb. In those days, there was nothing that men could do to protect themselves against the last random shots in the cosmic bombardment that had once scarred the face of the moon. The meteorites of 1908 and 1947 had struck uninhabited wilderness, but by the end of the 21st century, there was no region left on Earth that could be safely used for celestial target practice. The human race had spread from pole to pole, and so, inevitably. At 09:46 GMT on the morning of September the 11th, interesting how he picked that date, isn't it? Of course, it's completely coincidental. In the exceptionally beautiful summer of the year 2077, most of the inhabitants of Europe saw a dazzling fireball appear in the eastern sky. Within seconds, it was brighter than the sun, and as it moved across the heavens, at first in utter silence, it left behind it a churning column of dust and smoke. Somewhere above Austria, it began to disintegrate, producing a series of concussions so violent that more than 1 million people had their hearing permanently damaged. They were the lucky ones. Moving at 50 kilometers a second, 1,000 tons of rock and metal impacted on the plains of northern Italy, destroying in a few flaming moments the labor of centuries. The cities of Padua and Verona were wiped from the face of the earth, and the last glories of Venice sank forever beneath the sea as the waters of the Adriatic came thundering landwards after the hammer blow from space. 600,000 people died, and the total damage was more than $1 trillion. But the loss to art, to history, to science, to the whole human race, for the rest of time was beyond all computation. It was as if a great war had been fought and lost in a single morning, and few could draw much pleasure from the fact that as the dust of destruction slowly settled, for months the whole world witnessed the most splendid dawns and sunsets since Krakatoa. After the initial shock, mankind reacted with a determination and a unity that no earlier age could have shown. Such a disaster, it was realized, might not occur again for 1,000 years. But it might occur tomorrow, and the next time the consequences could be even worse. Very well, there would be no next time. 100 years earlier, a much poorer world with far feebler resources had squandered its wealth attempting to destroy weapons launched suicidally by mankind against itself. The effort had never been successful, but the skills acquired then had not been forgotten. Now they could be used for a far nobler purpose and on an infinitely vaster stage. No meteorite large enough to cause catastrophe would ever again be allowed to breach the defenses of Earth. So began Project Space Guard. And let me talk a bit about Space Guard in this. Of course, what now is asteroid impact. I'm going to spend a bit of time on this. It's well, I lose a bit of my levity in this talk, I'm afraid. And Arthur C. Clarke wasn't the first one to do this. In 1897, H.G. Wells wrote a short story called The Star, which is a similar thing. So human beings have been aware of this possibility for well over 100 years. So let's just go through our normal process with these things. So what are they? Lumps of rock, effectively a meter to 500 kilometers approximately in diameter. How frequent are they? Well, let's have a look. This was the inner solar system in the year 1800. This is what we knew about what was basically between Mars and the Sun. And there's, apart from Earth's moon, we just got the Earth, Venus, and Mercury. Nothing else. Next year, of course, was when Ceres was discovered. But within 100 years, this is all we had discovered. And anything in red is something that is potentially crossing Earth's orbit. So this is something that is essentially potential, anyway, of interaction with the Earth. By 1950, the year I was born, it looked a bit like this. We had a few more, and certainly quite a few more red ones around the place. This, of course, is certainly what triggered Arthur C. Clarke to write his story. By the time we're in 1990, it's like this. Of course, the dots aren't to scale size. It's only the number that's to scale. And by the time we get to 1999, which is the latest I've got for this, it's a bit like this. There's a heck of a lot of stuff out there, and there's absolutely no point in going any further, because 2 years after that, the whole thing would just be, the outer bit would just be a solid block of color. So this is asteroids. And there's essentially two ways they can get us. The first way is an Earth impact, an Earth strike. And this is the sort of thing that took out the dinosaurs, the Chicxulub crater and Yucatan. An enormous amount of damage. And we've got these things actually around Europe. There's Rochechouart in France is a big crater. And there's the Ries crater in Germany and various others. We're finding more and more satellite imagery of the Earth's surface has shown us quite a lot. The other way is when you get an airburst. Best animation of this I could find, actually. I apologize that it's in Italian. At least I assume it's Italian. I don't speak Italian, so I wouldn't know. It comes in, this meteoroid, it comes through the mesosphere, but as it hits the stratosphere, it starts to break up. And you get an explosion in the sky. So this is the sort of thing which happened at Tunguska, we were talking about earlier. Now, there are eyewitness accounts of this, not of the actual fireball itself, but of people who were certainly within the blast range. They're talking about people being blown into trees and breaking limbs and things like that. Fortunately, because it was in this very, very unpopulated region of Siberia, hardly anybody was injured. There is no, as far as we are aware, no impact crater. So it's almost certainly an airburst. And further evidence for that was when they eventually went to look at the site where it had happened. The trees away from it were all radially chopped down, knocked down outwards, but those underneath, a lot of them, as shown in that lower image there, had just had their branches stripped off as the blast had actually come down, and in a lot of cases, the tree trunks themselves were left vertically standing. And that was a 15 megaton blast. It's being calculated at, and remember the Hiroshima bomb was about 20 kilotons, so we're talking about something nearly 1,000 times with the power of our first atomic bomb. I think, okay, well, that's there. There was the Sikhote Allen one in 1947. It was pretty good luck that nobody had their satellite monitoring for nuclear explosions going by then, or aircraft monitoring. Satellites came only a decade or so later, a bit more than a decade later. But because it would almost certainly have been thought to be in a nuclear explosion. That was the Sikhote Allen one at Vladivostok, and could, had it been detected, have triggered a nuclear war. But the one we remember is the one that happened about nearly 8 years ago now, because we were all looking, we were all expecting to be able, or hoping to be able to see night a satellite come within the orbit of the geostationary satellites around the Earth. So we see an asteroid come within that. I can't remember its designation. It was 20 something 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 something. Doesn't really matter. That morning, this thing the size of a building came down near Chelyabinsk in Russia. Fortunately, lots and lots of people, because of car crash scams, many more than here at the time, had dash cams. And so you've got a lot of security camera footage and dash cam footage going this. So what we had is something about the size of a building and about a 500 kiloton blast. So, you know, sort of still pretty blooming big. You know, 25 Hiroshimas there. Just if you can, turn your sound up for this. It's much more effective. What you get from that is the beginnings, I think, of a sense of what it must have been like. Certainly this enormous flash in the sky. Slightly fewer than 1,500 people were hospitalized. Almost all of them lacerated by flying glass. Because what happened was people saw this bright flash in the sky. It was a winter morning. Went to the window to have a look. And of course, light travels much faster than sound or shock waves. And then the shockwave hit and blasted the window in. The heroine of the hour was a primary school teacher who saw this flash in the sky and thought, oh, it's an opportunity for a nuclear drill, told all the kids to get under their desks, which they did. And although the windows were blasted in and flying glass all over the classroom, not one child was injured. So I guess that's brilliant. She herself had a lacerated arm and needed stitches, but, you know, that's good. So, you know, sort of human ingenuity does come around for that. To give you some idea, though, of the extent of what these things are like, had Tunguska hit a built-up city, say London, that black line there is the devastated area of Tunguska. It's that shape because the impactor was coming in at this angle, so it was sort of pulling its destruction cone that way. So effectively, if it was London, everything inside the M25 would have just been flattened. That's the sort of thing we're talking about. This is the potential, and this was not a big one. This was not a big one at all. So what can we do about these things? Well, you get loads of ideas. Some say, well, if we realize one's going to hit London, we just evacuate. Can you imagine trying to evacuate 10 million people? And if you evacuate them, what are you going to do with them? The next thing is sometimes called the Bruce Willis scenario, Armageddon. You destroy them. Well, no, that's probably one of the most stupid things you could do, because what you're doing then is you're turning a predictable single impactor into a cluster bomb, and which is much less predictable and ultimately won't have any less energy as it hits the Earth. Or you can deflect it, and that's where the serious money is going at the moment. And I mentioned Space Guard earlier. A man called Jay Tate, ex-military man, has many years ago now, many decades ago now, started an organization called Space Guard UK. And he's got a place up at Knighton in Shropshire, I think it is, so just north of you guys, where he's installing telescopes for asteroid hunting and that. And he's also talking, trying to talk to governments that they actually need to do something about it. And of course, there's things like the linear program and stuff, Lincoln Near-Earth asteroid stuff as well. So people are sort of taking it seriously, sort of, but Britain actually isn't really, but we'll come to that a bit later. So if we're going to look at what the effect of something like this is, and this next bit is courtesy of Jay Tate of Space Guard. I'm using it on with his blessing. If we're trying to work out how much we should be spending to mitigate a threat, one of the ways of doing it is by plotting the interval between events and the number of deaths each event causes. And there are several regions of this graph which you think, well, okay, so there, if something is causing, say, as we are here, fewer than 100 deaths, or around about 100 deaths every million years, well, we're probably not going to spend a lot of money sort of trying to mitigate that threat. There's what's called the local scrutiny line, and then there's things that we think are intolerable. So if something's causing, say, 1,000 deaths every 10 years, then it might be something we think that actually might be worth spending a bit of money on to do something about. So we've effectively got three regions. Here we're not going to do anything about. Here we really need to. And in this region here, well, it's a case of it depends. So let's put a few things on there. So the idea is try to get things as low as reasonably possible. So something like a Chernobyl RBMK reactor before 1986, before Chernobyl went bang, it didn't actually quite go bang, but you know what I mean, would have been up here, certainly in the intolerable. Money has been spent to bring it down to here. So that is considered to now be okay. Aircraft crashes around here, which is why we do try to mitigate against aircraft crashes. If Tunguska hit a major city, that's the one I showed you with London, it would be here. So it's probably only every million years. It might take out 1 million people, but actually on this graph, it's not considered to be intolerable. It's we'd have to spend an enormous amount of money on trying to mitigate against it. And that's part of the things going on with the COVID thing now is, you know, how much money is it actually worth spending? A 1 kilometer impactor, on the other hand, and there are lots of 1 kilometer ones out there, although we think we've got them all, but we don't know for certain, would be there with its tsunami threat there. So depending on where it hit. So that is definitely something we need to be thinking about and thinking about mitigating. So let's take a 1 kilometer impactor, and the best calculations, predictions, modeling we have says we'd expect one about every 100,000 years, that it would kill about 25% of the population. So in UK casualties, that's about 15 million people. We each have a cost on our life, at least while members of the, or when we were members of the EU, which, you know, people like me, sort of at the grey end of life, are probably the low end of that. And the, you know, people at their economic prime, their lives are worth a lot more, around about 3 million quid. So let's just take something approximately in the middle of that. And we say about, you know, about 1.5 million quid. And well, if we take those figures, then the total cost is 22,500 billion, the actuarial cost of these lives, if we're going to do a cost-benefit analysis on it, which is an enormous amount of money. If we divide that by 100,000 years, that means 225 million quid. If we're spending 225 million quid a year on this, we're breaking even. So how much are we spending? And remember that this figure only includes, I say only includes, the actuarial cost of human life. It doesn't include cost of property, heritage, commercial losses, economic damage, anything else. It is purely the cost that actuaries put on human life. Okay, well, the latest year for which I can get data for is 2018-2019, and the entire UK Space Agency expenditure was 375 million. Of that, well, UKSA actually doesn't do anything for asteroid mitigation. It does it through the ESA, European Space Agency, and the annual contribution to that mitigation is in the order of single-figure thousands of pounds a year. I think it's, you know, we can see, you know, politicians tend to think in terms of the next election and not the good of humanity into the future. And that's not party political, that's all of them. So what can we do about it? There are various things. Well, the deflection with something has come about. You know, we've had these ideas, you know, you can send up lasers there and you laser it on one side. Well, I think, forgive me if I'm misrepresentative, but I'm sure Brian Cox was one of those who came up with the idea. You go out there, paint half of it white, because asteroids tend to be about the same color as coal. So you paint half of it white, and solar radiation will differentially interact with it, and it only needs to deflect a tiny amount. Remember those huge distances involved related to the size of the thing. So we only have to tiny amount of deflection. Or the other another option, we just park something very heavy next to it, it'll move. Remember Apollo 13, when they were coming back to Earth in the movie, if they hit the atmosphere too steeply, they're going to burn up. If they hit it too shallowly, they're going to skip off. You know, it's a very, very small margin of error that you're allowed before you miss. And things do bounce off and miss in that sense. You know, this does happen. So one of the things that ESA and NASA are putting up is they've got this what they call their AIDA program. I'll show you a little video on that. Just to give you a pre-warning, because this is an international collaboration in their publicity movie, they have people representing all the nations involved, so, or certainly most of them, so the accents change rather a lot. Here we go.
On February 15, 2013, the world saw the results of a small near-Earth object entering our atmosphere. The high-altitude explosion of 500 kilotons TNT energy, triggered by the impact of that 17-meter object, injured more than 1,500 people and caused extensive damage to Chelyabinsk, Russia. The necessary first step to defend the planet from the asteroid impact hazard is to discover those large near-Earth objects that may pose a significant danger. The US and the European Union both have search programs, but what can we do if an asteroid is discovered that is about to hit the Earth? One mitigation approach is to deflect the asteroid, hitting it with a spacecraft and pushing it off its collision course. But this method has never been demonstrated. The Asteroid Impact and Deflection Assessment, or AIDA, is a joint venture of NASA and the European Space Agency to monitor, strike, and ultimately alter the orbit of Didymos, a binary asteroid. AIDA consists of two independently launched spacecraft, an observatory and a kinetic impactor. The US component, DART, is the kinetic impactor that will hit the asteroid in order to deflect it. ESA would build and launch AIM, the observatory, which will survey the targeted binary asteroid before and after the collision, measuring the deflection precisely and determining key physical properties of the asteroid.
Designed, built, and operated by the Johns Hopkins Applied Physics Lab, DART will be the first demonstration of kinetic impactor technology for asteroid mitigation.
DART will impact its target at about 6 kilometers per second relative to the asteroid, about 9 times faster than the bullet from an AK-47. The required targeting precision has been demonstrated by 2 intercept missions led by APO. First, the 1986 Vector SUM space-based intercept of a thrusting vehicle, and second, the 2008 Burnt Frost sea-based missile interceptor satellite. And in 2001, NASA's NEAR mission, led by APO's Andrew Chang, achieved another first, successfully landing on the asteroid Eros.
We learned a great deal from NEAR's mission to asteroid Eros. Now we want to learn how to deflect a near-Earth object using a spacecraft impact. When DART collides with a smaller secondary member of Didymos, AIM will measure the change in its orbit, and that data will be crucial to prove we can change the trajectory of an asteroid on a collision course with Earth.
AIM will measure very accurately the amount of the deflection, but it will also characterize the surface properties of the asteroid and its interior structure. This information is required to characterize the physics behind the impact and to prepare for a possible future mitigation of an asteroid impact by spacecraft kinetic impactor. AIM will demonstrate the payload and spacecraft technology required to operate nearby the asteroid and to observe the impact and characterize the impact dynamics very accurately.
AIDA is a unique international collaboration where the two separate missions each have independent value. In fact, should only one launch in time to rendezvous the asteroid Didymos, the science return will still be significant. For instance, if DART is launched alone, the asteroid deflection can still be measured by observatories on Earth. By operating together, AIM and DART will provide data that will answer a great deal of questions about everything from orbital and impact modeling to theories about asteroid composition and material. The mission's two sections each will draw upon the respective strengths of the team designing and flying them, and will provide invaluable data regarding asteroid deflection technology as a viable means of planetary defense.
AIDA will leverage the respective strengths of the European and US space agencies and space communities. Humanity needs to know how asteroids will react to deflection. AIDA will give us our first real answers to the question, what can we do if an asteroid is about to hit the Earth?
Well, that's one way. The Space Guard suggestion is something very different, and it is based on technology that we already have, we know exists, and we know we can do. And is something that could be tested very, very quickly. It doesn't need something as complicated as the AIDA mission. It could already have been used, actually, if there's just been the will behind it to do it. We know how to deliver something to an asteroid. I mean, it's been done many times. And then how do you deflect it? And this is something that is possible with something that was developed in the Cold War, something I think they call it the enhanced radiation device, commonly known as the neutron bomb. And it was a nuclear weapon that was designed to have an enormous amount of radiation in comparison to its explosive power. The idea is that it would, if Soviet tank crews were coming over Europe, you could disable the tank crews without destroying a heck of a lot of property, so someone then unfairly described as the ultimate capitalist weapon, because it kills people but preserves property. Well, it actually wouldn't actually preserve property, but yeah. But what you've got is you've got an enormous radiation pulse from this. And what I think the smart money is on is something like this. And the example here is that what you have is you actually have two explosives. One is very close, and it creates a small crater, shown as much bigger than it would be here, but it creates a crater. You've got to be very careful that you don't actually destroy the thing, because that's the thing that you're then turning your single impactor into a cluster bomb. And then your bigger one, they're using the crater as almost to help as almost like a shaped charge, I suppose, but not quite, of course you'd be pushing it the other way. Then enhances the deflection effect of the larger explosive, and that I think is where the sensible money is going, because we've got all the technology, and if something would look like it was going to hit in 2 months' time, it's something we could certainly do. There is absolutely no way we're going to get the AIDA Didymos thing set up and working in that sort of timescale. So that's it. So I think there is hope. It requires political will, as does everything else. I said I wasn't going to mention COVID, but actually I'm going to, because what has happened with the COVID crisis, what has shown us is that when all of a sudden money becomes no object, all of a sudden as a species we can do something. You know, to get a vaccine out within effectively a year is pretty blooming good. And that's because nobody's had to apply for funding or anything like this. There hasn't been all that sort of stuff going on. And there have been, because people realize the thing, you've had hundreds of thousands of volunteers, not the problems drug trials often have, just recruiting a few hundred people. So it's been made. So I think human beings could do this. I think ultimately we have it in us to do it when we know we have to. So that's number 9. So we might have survived all those cosmic attempts to wipe us out, from outside, from inside. But there's still one more little trick it's got up its sleeve, the universe. The sun, as a main sequence star, the size it is now, but it will eventually become a red giant. When it does, it will have a diameter of approximately 2 astronomical units. So its radius is 1 astronomical unit, which is essentially the distance of the Earth from the sun. So if nothing else changes, we would end up on the surface of the sun. So what happens is this, a little bit of basic solar physics here. Stars are a dynamic equilibrium between gravity pulling inwards, which effectively is what drives the whole thing, and nuclear pressure pushing outwards. So you've got this dynamic equilibrium going on. As the reactions in the core eventually peter out, as they will do, or they will start to do within a few billion years, gravity takes over. And so it will compress the whole thing, which again, that heats it up. And you'll then start getting helium burning, but that will happen throughout the body of the star. And that makes it expand enormously, and that's where you get your red giant from. Now, most people seem to think that the sun will get us when it becomes a red giant, which is about 5.4 billion years' time. That's actually not true, because there are a few things going to happen between now and then. We will not actually end up as the surface of the sun, because as the sun enters its red giant's phase, it's going to be losing an enormous amount of mass. As it loses mass, Earth's orbital radius is going to increase. So as it increases, we no longer end up at risk of being engulfed by the sun. So we may be safe then. Well, no, if you think that, probably haven't been paying attention, because the universe is out to get us, and the universe will get us. Because about 3.5 billion years before it enters its red giant's phase, it's going to double in size over about half a billion years, 500,000 years. Sorry, 500 million years. And it will become a subgiant. And when it does that, its luminosity will double. Its luminosity being its total output. Okay. When that happens, Earth will become hotter than Venus is today. It means we've got a surface that's hot enough to melt lead. The oceans will disappear. They'll just be boiled off. Oxygen and just about most of the other stuff in the atmosphere will almost certainly achieve escape velocity. So that'll happen. So essentially, we have no world as we have it today. So what can we do about it? And the answer is nothing. The risk? Well, it's going to happen. We've got about 2 billion years left if we look after each other until then, for that long. But that's about it, folks. Which might sound sad, but let's look at it this way. Final score. Now, if we have survived all those other attempts to wipe us out, as it were, in the time, we've got humanity 9, universe 1. Okay? So, do we win? Nope, we still lose. Because, as I should have told you at the beginning, the universe is going to get us right out.